All right. Welcome to the last video of the year, and I guess of this series for separation, this course of separations. This last video is going to be about the MESH distillation calculations. So these lists, or I guess a set of distillation calculations for the MESH equations. I believe MESH stands for material, equilibrium, summation, and heat. So it's a set of equations that we have to solve for in order to find the, I guess the most simplest way is just to say to solve our distillation column. So so let me just switch to the online collab here. I have a list of references. So according to this online lecture I found, so yeah, mass, equilibrium, summation, and heat. So we have our material balance, our equilibrium relationship. So in our case, we'll be doing the Raoult's law, non-ideality. So we have that gamma function and RTL. Summation, dealing with mole fractions, and the heat is the energy balance. So it says that they are not trivial to solve, and I believe, as far as I'm aware of or I've been told, this is not done in any undergraduate course for most colleges. So that's what we'll be doing today. We're going to be coding those out, and we'll deriving them, coding them, and then eventually having that solved. I believe the question is asking here, we'll be needing to generate that binary XY diagram. Well, specifically, we have our equilibrium curve, which is our binary XY diagram, and then we have our staircases, which we've done multiple times now. Just a heads up, I'll be I have a lot of references here, but I have some pieces of code that we'll be referencing. We've done these in previous videos, but the most important thing here is the template I'm using, since some of these functions we have used, we've coded them out, some of them we haven't. So I'll try to explain that best I can. Don't think I'll need the iPad for a while here, so I'll just try to keep it on. But yeah, let's just get started. So we have our mesh calculation. I'm going to go ahead and run this. This is my template. I'm using it to practice and such. So for our imports, just to kind of jump straight into it here. Make sure I'm centered and we're recording. Okay. So pretty basic imports. We've had these most classes, most videos. Our CHE tools from our GitHub repository, NumPy, Jax NumPy as well, and then the 64-bit, so we maintain that precision. We also have root scalar, minimize scalar bracket. I think root scalar and root have actually only been used in the functions that I'm about to explain and not in future functions. Minimize scalar and bracket we will use, I think, at the very end. We'll be needing to bracket and minimize a multiplicative factor t for our delta unknown, so that'll make more sense later. We have xbit logit functions, so those are squashing, and the inverse of the xbit is the logit, so it reverses it back to the normal range of -infinity to infinity. I'll explain that where it's used right here in the following functions. Plotly for subplots as we normally graph. That'll be our staircase, our McCabe-Thiele essentially, and our binary XY diagram. And an interpolator, which I don't think we actually use. And then I have the set print options. So we have the number of digits, 5 digits in this case. And I think before I forget, I think line width of about 500 is pretty good. So we have the array stacked up all the way from left to right before it goes to the next row. Yeah, all this ran pretty well. So we're starting with our gas constant. This is used in, I don't think it's used in the gamma function, but it's used down here in the Clausius Clapeyron. So I'll get to that. For our binary mixture today, we have ethanol-water, but once we have the mesh calculation solved for this system of equations, technically we could input as many as we want and it would still work. All we would have to change is the composition. So I think at the very bottom we have 50-50 for Z denoting whether it's vapor or liquid. So 50% mixture of ethanol water. So we need to adjust that and perhaps some other parameters I'm forgetting. But other than that, we should be able to run the mesh calculation just as easy with 2 or maybe even more. Now, this gamma function is something we've simplified a while back in a previous video. I won't reiterate all of that, but today's video, we'll be actually using the one in our GitHub repository, since that has some more optimizations for jacks, since we're going to be using the Jacobian, which maintains that we need to make pretty much everything in terms of jacks so that's compatible, as well as just making things faster and having more precision. So with this gamma, again, we'll be using, I think we use the props tool, and so it'll be p.nrtl gamma or gamma nrtl, can't remember, but yeah, we'll be using that instead of this function, which we try to, I think the point was to get across how to kind of dismember a very complicated equation like this, and since we're going to be using it, we need to know how it works. So that was the whole point there. Due pressure and due temperature, these are the ideal forms. So if you remember way back, the first video of this year, I think of this class actually, we did this. We had to kind of maneuver or move around some algebraic expressions, but eventually we were able to solve for their corresponding due pressures and due temperatures. So with bubble pressure and bubble temperature, you notice that we don't have the ideal forms. We're actually using the ideal forms for due pressure and due temperature in the NRTL forms. So it's a little bit more complicated with the dew points. But with the bubble points, all we have to worry about here is, since we already have an equation in a Raoult's law relating the gamma coefficient, so that's where that NRTL is coming from. It's essentially that non-ideality, that pairing between pairs of chemicals. In our case, it's only one pair, but remember the order does matter. So again, refer more back to that video if you want more details, but we already have that equation. So all we had to do is insert it into our Raoult's law and we could solve it as normal. Bubble temperature here, we got a little bit creative, or kind of overkill, I should say, in class, where we coded out this entire guess using the Clausius-Clapeyron. And if you remember what that looks like, it's like this. So I just pulled up a random thumbnail for a YouTube video, usually relating to pressures, but in our case, we solved it for a temperature given standard pressure and standard temperature. And of course, we knew our heat of vaporizations given a composition and just given a composition and temperature. So, and here was where that R gas constant was being used, as I mentioned earlier. So we kind of moved everything to one side and solved for the temperature here. So I'll get rid of these two here. So that's what this guess is about. Again, you could probably just input a pretty arbitrary guess and it would still work, but kind of just wanted to have fun, I guess. So again, the bubble temperature was reiterating this function where we use our bubble pressure to get some sort of guess for our temperature, and using that temperature guess, we had a temperature guess and we input that into this root function, which is reiterating, and then we solve for it to get our actual bubble temperature given a pressure. So using that root scalar function, we again just copy pasted and found our corresponding temperature. And remember, for all these bubble points and dew point functions, we always output the opposing mole fraction. So with the bubble points in general, we have a saturated liquid, so we're looking for the first point a bubble forms. So we're inputting at a saturated liquid that has to correspond with a corresponding liquid mole fraction, and we output the vapor mole fraction. And of course, conversely, for the dew points, we output a liquid mole fraction. So hopefully this is zoomed in enough you can see it, but that might be too much. But here's where it gets a little complicated. Actually, between the two, there's the only difference between dew temperature and dew pressure is that we're solving for pressure and temperature. It's actually pretty identical for the layout of it. So just to kind of start here, this is actually something we didn't do in a previous video. I think bubble pressure and temperature were actually done in the Pontron-Savart, if I remember correctly, somewhere up here. Yeah. Can't remember exactly what it was for, but I think it was just for the, just the equilibrium here. So we needed the bubble pressure to use as a guess for our temperature. So that's why we have both here. Again, previous video. So with the dew points for the NRTL, the problem here is that we don't have an equation relating without a liquid mole fraction, how to get our vapor mole fraction. So the idea here is that we use two equations. We have two unknowns, and that matches with our degrees of freedom. So doing that, we solve for those two equations. So we have fugacity. This is Raoult's law. Since they're normally equal to each other, we subtract since we want this relationship to be true. And then our other equation here is our summation of mole fractions. Now, the key here is this idea of xbit and logit function. I mentioned these before in our imports. So the xbit is a squashing function. I don't know if I have that pulled up. I do not. So with xbit, I think I can just say xbit function. Should pull up kind of SC curve where it, yeah, right here. It kind of, I don't know what's the best way to explain this, but it squashes any range of values for from negative infinity to infinity and squashes them to 0 and 1, which matches exactly what we want for our mole fractions. So the reason why we're doing this is because the root function itself doesn't bracket these values, so it can actually explore values that go beyond 0 and 1, meaning it could explore values that are negative, it could explore values that are greater than 1, and we don't want that for our liquid mole fractions or mole fractions in general. Liquid mole fractions, because we're doing a dew point, so we have to solve for that liquid mole fraction. So instead, what we do, we have this guess from our ideal versions. So we have those equations from before. I mentioned those prior, and we use those as a guess. Remember, we're getting a pressure in this case for our dew pressure, and a guess, we output that liquid mole fraction. And we put those in a vector, concatenate them row-wise, and use the root to solve it with those initial guesses. So basically reiterating this and solving for this vector of unknowns. And after that, we have a little practicality function here, just saying if it doesn't work. So that's how we discovered the need to have an xbit logit function, is because our root function kept failing. So that's why we added those. And then now we output, well, correspondingly, we have our pressure as a first attribute like we always do, and the x, so liquid mole fraction, since we're given a vapor mole fraction. So again, same exact scenario, except we have temperature instead of pressures here. Now here's where it gets a little bit dicey. I don't think we've ever talked about flash calculations, but essentially for the ideal version, well, a flash calculation I should start with is when you have some sort of feed and it separates at, so think of a feed going into this box, and that box is at a certain pressure and temperature. And because of that feed, whether it's coming in as a vapor or liquid, it has to separate. Well, it should separate if that pressure and temperature is within the bounds of its, well, separating points. So bubble pressure, dew pressure, and all those things. So with that being said, to solve for a flash calculation, we're solving for I guess I should say we're given a composition and a pressure and temperature. So isobaric, isothermal. Given that composition, we want to solve for these mole fractions, and then there's this idea of a vapor fraction. So that's where the Rashford-Rice comes in. We did this in class, and I'm debating whether or not. Yeah, I'll just pull it up from class here. So go here, something like this. Actually, let's do a split here. And like so. Let's do a main. Okay, so you can see my cursor. This is way back, I think 2 months ago, but right when we were talking about NRTL. So this idea of a flash calculation, let's see if I can find it. This one, here we go. So this kind of is going into the loads here. So we go back to this proportionality constant. We've talked about it before. It's our y over our x, our vapor mole fractions over our liquid mole fractions. And you notice that simplifying it down after we substitute in the Raoult's law for the vapor mole fraction, we get our saturation vapor pressure over total pressure. So that's where we get our K. And now for non-ideal, we have this idea of gamma, which is down here with the NRTL version of our flash calculation. So more on that later. This idea of Rashford-Rice, so yeah, I don't think I showed the derivation or anything here, but it's an equation and there's some algebraic derivation to it, which I won't go over. But essentially, it's this equation where if we know our composition, we know our proportionality constants, and we know our vapor fractions, we can solve well, I guess I should say we're solving for that vapor fraction, and the sum of all of these, so this applies to every composition, or I should say every chemical involved in this distillation calculation, or I guess flash calculation, sorry, misspoke there. We're solving for this vapor fraction since it's a sum of this expression, and solving for that allows us to then back substitute, which I don't think is in here, but might be in my notes. We do a back substitution after we solve for that vapor fraction. So right here, we have our z, and that's exactly after here. Once we get our vapor fraction, which we do with defining it as a function, and then using a root scalar to find that singular value. And we bracket it between 0 and 1 because this vapor fraction, of course, has to be, it's a fraction, it's between 0 and 1. So once we have that vapor fraction and we have our proportionality constants, we can rearrange this balance here. So this is our liquid mole fractions and our liquid fraction, and a vapor mole fraction times our vapor fractions. So we know this vapor fraction, we can arrange this liquid mole fraction as, well, it's 1 minus the vapor fraction, rearranging the y in terms of, or from the proportionality constant, then we can solve for x here. So kind of glossing it over since it's not the main focus here. Hopefully try to get all of this explaining done within the next 10 minutes or 5 minutes. Yeah, that's what that's doing. Now with the flash NRTL calculation, you would imagine it kind of follows the same steps as the due temperatures and due pressures, since we don't have a way to acquire that liquid mole fraction, since that's what we're solving for. So now there's this idea of trying to get a guess along for that liquid mole fraction, and doing that we assume we're mapped on a separation between our bubble pressure and due pressure in this case. So it's some sort of slope that we mapped ourselves on given a pressure. So that's this right here, and that way we're allowing ourselves, or I guess we're giving ourselves a way to get this liquid mole fraction, even though it's not technically correct. It's a sort of proportionality between the different absolutes, you could say, or a range of the separation for the flash calculation. So with that guess, now we can iterate our previous function. We have our gamma now with our k, which we saw earlier, since with non-ideality, we have this gamma function that we have to solve for. And remember that gamma takes a liquid mole fraction, so that's why it's inside the loop. You need that x guess to iterate. And of course, you need that temperature. So it's pretty much the same thing up here, except we had this little tidbit up here where we needed to use our, well, in this case, due pressure and bubble pressure to solve for these, or start with some sort of liquid mole fraction guess. And in doing so, we were left with solving that x once it's below a certain, I think it, yeah, once it's below a certain tolerance here, so the norm or absolute value of that component. And then we, again, just solve for our y, and now we have the same exact components we were trying to solve for. And I guess we also have iterations here, just to see how many iterations it took. So that is that. 20 minutes, not bad. Now the initial values here is what all those calculations kind of boiled down to. We didn't really need to do all of them. We could have just set numbers here, but figured since we did them in class, might as well use them here. So starting off with this this properties of this size. So if we actually look at this, this is returning a integer, and that is based on our ethanol-water. So if we look at size, that size of that array is 2. But if we actually look at what it's doing, it's saying what are the molecular weights of ethanol and water. So I actually can change this if I go all the way back up here to our ethanol-water, and I put this right here. Let's say I add another component like methanol, and hit Shift Enter, and now this should be giving us 3. So notice that however many excuse me, chemicals we have, that's how many, wow, excuse me, how many values we're outputting here. So for now, we're going to keep it 2, since that's what we did in class, and that's what I practice, and that's what we're going to do. So there we go, back to 2. Next we got here, again, this is pretty arbitrary. There's some other ways we could just hard code this to 2, but figures it automatically updates, so we'll just use it for convenience. Now, I think this comes from the problem statement, but I'm not too entirely sure. Some of them is included, some of them isn't, but well, we're basing it off of what we're given here. So the feed flow rate is 2 moles per second. Again, I mentioned our composition is 50-50, but it could be vapor or liquid. We're using Z to denote since that's our standard here. Pressure here, 100,000 pascals, and now we extract our dew temperature and bubble temperature so that we say that our feed temperature is in the middle of those two. So it's an average. That way we know it separates for sure, and it's not just at one point or either of the absolutes. We use our flash NRTL calculation to find the X and Y, so liquid mole fraction, vapor mole fraction of our feed, and then we also have our vapor fraction of our feed. That way we can discern how much percentage of our feed or how many moles per second that flow rate is vapor or liquid of that feed. And then we have our enthalpies since we know our molar flow rates, and we have our vapor fractions and our molar fractions. We can find our enthalpies. Remember that this comes from, it's just a property from our CG tools GitHub repository that allows us to have, or allows us to find the enthalpies given the number of moles of liquid or vapor correspondingly. So this one's liquid, other one is vapor. So base it off moles given a temperature, of course. So that could change. What else do we have? So these are our degrees of freedom. Yeah, let's go back to that. We can do a split again. I think I'm going to be doing this a lot. So if you remember in a previous assignment, or I guess video, we talked about, oh, my mascots, the degrees of freedom that we could use that are standardized. This was one of the ones we used. Can you actually see my screen? Oh, okay, cool. And today's video will be using this right-hand side, what I'm, I guess, highlighting with my cursor. So we have the condensate at saturation vapor pressure. Remember, we have 5 degrees of freedom, and these are what are typically used so that our distillation column converges. We have a solution for it. So condensate at saturation temperature, what does that mean? That is saying that we have a total condenser, and if it's at the saturation temperature, the vapor going up must become a saturated liquid. So that's something we'll be using here, or our reflux temperature. Well, that is our reflux temperature, I should say. So again, the vapor going up is condensed fully since we have a total condenser, and it goes to the saturation liquid or the bubble point of that vapor composition. And doing so allows us to solve for the power of the total condenser instead of trying to state it right away as a given degree of freedom. Other things here, we have the number of stages above and below the feed. So we've actually specified where the feed is. So that's inherently covering both of these two. Reflux ratio, we have that straight out, right, defined. We just need to be above our minimum reflux. So we just define it as 5 since why not? So remember that's reflux ratio is our reflux over our distillate. So the liquid flow over our distillate flow. And then distillate flow rate also specified as 1. So we made sure that is less than our feed. So it's actually half. So, and then our bottoms here is constricted since what goes in must come out. If we know our feed, we know our distillate flow, we should know our B total, which should be just 1. Unless I'm hallucinating. There we go. Perfect. All right, so that is everything explained. It only took 20 minutes. So let's do the actual assignment now. What are we doing? We're doing the mesh calculations. Okay. I have a feeling this will be a long one, and hopefully I don't make too many mistakes. So yeah, let's get this started. What we're starting with, we have a vector of unknowns. So what we'll be doing is we have 2 C+1 equations. Remember, a material balance or mass balance, energy balance, and equilibrium relationship. So we have C mass balances, a mass balance for every component, in our case 2. We have C equilibrium relationship. So that's the Raoult's law of non-ideality. So that's also 2, since we have 2 components, and then 1 energy balance. So 2 plus 2 plus 1, that's 5. We have 5 equations, so we'll have 5 values of, or 5 unknowns that we'll be needing to solve for. So those unknowns that we're going to be using, we have the flow rates. We have C flow rates, or C liquid flow rates, and C vapor flow rates for each component. So 2 liquid flow rates and 2 vapor flow rates. Of course, normally we have a liquid flow rate going down, which is comprised of the individual C flow rates. So we have 2 liquid flow rates technically and 2 vapor flow rates. And then we have a temperature that we're specifying. Since this is a constant pressure, what we're assuming, since there's negligible pressure differences between each stage in the distillation column. So not constant temperature, but an unknown temperature for each stage. So we'll have some sort of initial guesses that we'll need to put in for those unknowns so that we can get this thing started. Let's define our unknowns first. So hopefully the iPad stays on, but all right. So our unknowns, let's see. So that's going to be an array. So it's going to be 5 values, 5 unknowns for each stage, and we have 10 stages. So 5 value. Let's start with the number of rows. So that's our number of stages, ns. And then we have 5 unknowns. So 2, what did I say? 2c plus 1. So 2 times, what did we say components was? nc. So 2 times nc plus 1. And I think I need an extra parentheses since it'll yell at me because I'm doing multiplication or doing math inside an array. So yeah, let's look at that. Perfect. Oh, I made it an array. I need to make it 0. I don't know what. I was like, that's the size of it. So yeah, it is a 10 by 5. So exactly what we want. Oh yeah, it's 50. So 10 times 5 is 50, but I want to know the row and columns. So 10 rows, 5 columns. Okay. So we'll keep that open down here. What else? I think we'll need putting in, I don't know, putting values in, putting guesses in the unknown. Sure. So we'll need to, so it's full of zeros right now. We'll need to fill that up with our actual values. So there's some indexing there that needs to be done. But let's start with our initial guesses. So we've done this many times before. We have our balances. We'll assume constant molar overflow as an initial guess, which is perfectly normal. That's what we've done in the past for our McCabe Thiel. And well, that's what allows us to graph this in the first place. It's a binary system. So yeah, let's do our liquid total flows. The rectifying section. So remember that balance in the condenser. Well, actually, this comes from the reflux, so I don't know what I'm saying here. So start here. So remember, our reflux is L over D, and technically this is over D. I'll do some algebra on Python. Remember, this is at the condenser, so that reflux is what we're setting down. And if you have constant molar overflows, that applies to every section, every stage in the rectifying section. Consider it's above the feed, so constant molar overflow. And of course, below the feed is when it changes since you're adding, subtracting, vapor, liquid, etc. So if this is constant molar overflow, we have our liquid. So we rearrange this, so this is R times D. Okay. Now we can do our liquid total of our stripping section. So below the feed, remember liquid is flowing down. So the feed comes in, liquid flow from the feed has to add as we go down to our stripping section. So we have our rectifying section, which we add to our feed total. And we have to make sure that this is liquid. So we subtract 1 minus the vapor fraction. So now we have the liquid fraction of the feed instead of all of the feed. Of course, we only want the liquid portion that's coming down of the feed with the rectifying section. So we added that. So now we have our stripping section. Very similar is following for our vapor rectifying. So this is a balance of what we've done many times in the past. So the vapor going in has to have the liquid and the distillate coming out. So this is a balance at the condenser, but again, constant molar overflows. We say that the flow rates are the same. So what was it? The approximation that the heat of vaporizations don't change with composition. That's exactly the same thing as constant molar overflows here. So we're saying this is true. So this is again L0. We can say that this is L0, which it's the definition of the reflux ratio, but we rearranged it solving for the L, liquid molar flow rate. So we can just substitute R times D right there. And then we just factor out that distillate, so that we have R plus 1. So multiply R plus 1. And I think that is it. Then we have our, well, let me label these. We have liquid flow, we have vapor flow. So we need our stripping section now. So remember, with vapor, it's flowing up, so we have to add. So technically, if we think about it like, so the V total of the stripping plus our feed, that's vapor, is equal to V total rectifying. So for solving for this stripping section, we need to subtract our feed of vapor from our V total rectifying. So again, what's the best way to think about it? So we have our stripping section going up, stripping section going up, and our feed coming in. So whatever percentage is vapor comes along with it and goes up to the rectifying. So we're subtracting that from our rectifying to see how much was actually from the stripping. So subtract and make this capital. And we say that instead of 1 minus is actually just the vapor. So we can take out those parentheses. And it's the full vapor fraction. Yeah. I think we're good there. And the other thing, so I mentioned flow rates. Now we have to have our guess of the temperature. So temperature guess, so T guess maybe. Similar to how we did it up here, we took an average. So we're going to say, just because we can, let's say our condenser and our boiler are at the bubble temperature and dew temperature respectively. Saturated liquid and vapor correspondingly. We know that's true for the bubble temperature or at the condenser, but we have a partial reboiler. I don't know if that's shown here. So that'll be a equilibrium stage that we have to account for when we solve for each stage. But yeah, it's just an initial guess, so it doesn't have to be completely accurate, but that's what I'm doing here, so it makes sense. I'll do a linear space points. Normally we use this for plotting, but I'm using it here for space points between our bubble temperature and dew temperature. So starting with our bubble temperature, again, we want to start with our bubble temperature since it's the topmost, and we're going to be indexing from the top to the bottom. Of course, I could mess around with indexing, but it's easier if we follow the format here from top to bottom. So at the top, we have our bubble temperature, NRTL for non-ideality. We plug in, so remember our vapor is going up to be saturated liquid. So if we say that the mole fraction didn't change from our feed, we just say plugging in our vapor mole fraction. Of course, this is wrong, but then we have a temperature as well. Is this the, or I'm sorry, not temperature, pressure, since we're solving a temperature. And we grab the first component. Remember, the first component is always what we're solving for, and this is actually outputting a 2 value. So let me just put this here so we can actually see. We're not familiar if you don't remember. So these are 2 values, so or 2 arrays, I should say. So one is the temperature, the other is the, in this case, liquid mole fraction. So in this case, we only want the first attribute, or not first attribute, but the first array. So we index that with 0, and that should just give us the temperature. Coolio. Next thing we do is, so that's our starting point. Now we do our ending point at our dew temperature at the reboiler. Of course, this is incorrect. It's not a saturated vapor down there. It's a partial reboiler. But we do the exact same thing. So it's a liquid coming down that's about to be saturated vapor, which it's not, and at a constant pressure. And we also grab the first attribute. Now the last thing for linear space points is we need the number of points, so that'll just be the number of stages. So let's take a look at that. Should be going from, not subscriptable. What? Oh boy. Oh, I see. It's too late for this. Okay. There we go. So we go from low to high temperature. Makes sense, starting at the condenser down to the reboiler. Now, you plot this up. Or not plot this up, but we index these. So, we'll fill these out a little bit one by one. So starting with the liquid flow rates, we have the first two columns all the way down, and we have to make sure for the rectifying, stripping, respectively, rectifying stops at right before the feed, and stripping includes the feed. So to do that, we can do all the rows until we hit the feed stage, and then for this will be the same for both liquid flow rates. We want all the columns until we hit the third column, so we index to number 2, and number 2, remember, is number of components as well, NC. So that means we remember indexing is 0, 1, 2, 3, 4. So even though it's a 10 by 5, it's technically indexed from 0 to 4 and 0 to 9. So we index to 0 and 1. We don't include the last index. So for liquid flow rates, that would be liquid total rectifying, and then we multiply by, I think, just choose vapor mole fraction, just because. I'm actually not too sure why we did that in class, but it's an initial guess. We can say that the liquid coming down is more saturated in the other component, but I mean, there's not really justifying any of this since they're all not really accurate. It's just somewhere to start. So same exact thing for our stripping section. So now we'll mix up the mole fraction to the liquid mole fraction. And of course, not from the feed, but now starting from the feed to the very end, but we want to exclude the reboiler here. So let's actually just take a look at this. So yeah, we updated our values here. So, did I switch these up? I don't even remember what we did in class, honestly. That looks... You know what? I'll code this out all, and then I'll check it after a quick pause. But yeah, I'll code this out for all of them first. So you'll probably be asking, why did we stop right before the end? Remember, this stage is our reboiler, so we have to code that out separately. Just for the liquid flow rate, the vapor flow rate is the same. This is what we're assuming, just to be consistent with what we did in class. But yeah, let's do our reboiler. So this is the very last row. And the indexing is the same since it's the liquid flow rates. And now we say it's the total bottoms flow times, I think we can just say it's the liquid mole fraction. So we got that filled out. I think this is flipped. I don't know. I think I'm confusing myself. It doesn't really matter since it's going to change anyway, but if we're closer to the right answer, it'll give us less iterations. So, I mean, every time I've done this, I keep getting different iterations, so I'm not too sure where that's coming from, but anyway, so this was the liquid flows. We'll do our vapor flows next. I'll just copy paste this, honestly. So what are we changing? Now these are vapor flows. And then instead, the feed, where it stops and starts from the feed, is correct. That's the distinguishing point between rectifying, stripping, so we leave those. The difference is where they're starting from the columns, so we can say instead of ending at NC, ending at index 2, we go all the way until the end because we ignore this last value for all the stages. Remember, that's our temperature. So we'll do NC to the end. See that? Pretty good, except we don't want to end at the reboiler. Instead, we just go all the way. So don't ask me why. We just trying to be consistent. Again, these are guesses. They don't have to be accurate. Honestly, you could put anything, but remember they have to be relatively close to, or relatively realistic, I guess, for this thing to work. Since, again, when we take the Jacobian, we have to linearize these sets of nonlinear systems. Sorry, my voice is getting scratchy. So next we'll do RT guess here. Oh, okay. Here we go. Oh, 40 minutes already. Okay. Should I hurry up here? We have our T guesses. So that is all the rows, and only the last column. And then it's just our T guess, I think. Awesome. Yeah. I'll go ahead and pause this real quick to make sure I have the right values here. Okay, I think we're good. You might be asking why I'm so worried about these changes. It's that because I have a reference I'm using. I've done this like 2 or 3 times, and every time things are slightly different, so it helps to be consistent, even though these are all guesses, to make sure I did them correctly and I'm headed on the right track. Since if I do it differently, there's a chance it could go wrong. So that's why I'm worried about, I guess a little worried about if I'm getting the same answers as I got before. So looks like we're good there. Yeah, we have our unknowns. Now we have to define our stages so that we can solve for these unknowns. So remember, this is our unknowns at a current time. We have remember when we did Newton-Raphson and the Thomas algorithm, we have in our case, we'll have a delta V, a delta vector of unknowns. So I think we'll call it delta unknowns. So that's how much we have to shift these unknowns by, such that our equations, our big E, I think that's what we'll call those arrays, or a set of arrays. Our equations go to 0 since we're solving for those relationships to be equal, so we set them to 0. So that's our kind of mini root solver, if you will, but kind of a lot more complicated than that. So starting off, we have our stages. So, okay. Here we go, stage 1. So the way we're going to be defining these is that, again, we ignore the condenser. We're starting at the stage below the condenser since we know the condenser is a total condenser. So this logic will be used later on for the boiler, but for our stage 1, if we want to solve for our condenser, if we know the flow rate coming down from the condenser, then we can do a simple enthalpy of that flow rate at that temperature, so at that reflux temperature, and we'll find the number of, I guess, the power needed to cool that vapor coming in from the stage above. Yeah, or I guess from the condenser's perspective, the vapor coming in from that stage below it, how much power we need to cool that down to the saturated liquid temperature, or that bubble temperature. So yeah. Now for stage 1, remember we have the neighboring dependencies on how to solve for that stage 1. So to do that, we need some lists of vectors of these unknowns, since these affect the mass balances. It won't affect the equilibrium relationships, but it will affect the energy balances, since energy balance is based on the mass balance. In our case here, for a distillation column, I should say. So normally for any stage, it would be vector 1, vector, and vec2. So this is the, I don't know, the name, the way we named it in class. So vector 1 referring to the stage above, vector referring to the current stage, and vector 2 referring to the stage below. So if we look at stage 1 here, this is stage 1. There's nothing above, so no dependence above. Again, total condenser, we ignore it. We know how to solve for it once we have a vapor flow rate. So we remove that, and we have the current stage and the stage below. So those are the list of unknowns, just these two that we're going to be solving for. So to do that, we'll unpack those vectors. So let's start with our liquid and vapor flow from our current stage. So we unpack our vector. To do that, so we're unpacking this value of, or this set of arrays, or I guess it's just this one array for this one stage. we want the liquid flow and the vapor flow. So we've done NP split, I think, before. So we are going to split this. So make sure it's Jax since we're using Jacobian. Remember, this is going to be reiterated for our list of equations that we want to set to 0. So we split this vector, and we have to make an index only from these 4 values and split them in half. So make sure it's an even number since we're splitting in half. So we index from the start all the way to before the last, so everything except the last. And I think that's it. So we should return LV, and let's see if it's the same. So stage 1, we're plugging in our unknown vector, the first row, and the unknown vector of the second row. So that's index 0 and 1. Again, this is stage 1. It depends on itself and the stage below. So unknown 0 row, first row, or index at 0, and then unknown index at 1, second row. So let's see if that's right. We should get 2.81, 2.187, perfect. And the vapor flow right next to it, 3.38, 2.61. So these will be identical to the stage below it. Since now we're going to be using 2 to denote it. And now let's look at it. It should be the exact same. 2.81, perfect. 3.38. Yeah. Again, these are perfect. Again, these are identical because we assume constant molar overflows between each section, this rectifying and stripping section. Yeah, 46 minutes, we're not even halfway, so this will be a very long video. Okay, so what else do we have? Yeah, we unpacked our liquid flow rates. We need our temperatures, so let's do temperature and temperature 2. That is vector, the last value of the vector, so current stage, last value, and stage below, current, last value. So look at those. Always good to double check. That should be 352, 353. So did I do that? Yep, 352. Perfect. Now we have our equations. So one of them, we have our mass balance. Go one at a time. So mass balance, I'll comment that out for now. Equilibrium relationship, comment that out, and energy balance. So the easiest here might actually just be the equilibrium relationship. So that's the Raoult's law. We've done that before. Let me go find it. I think it's right here, actually. We're missing this bubble pressure. I don't know if we're missing it, but we're not setting it equal to something is what I'm concerned about. So, I'll write it out. I feel like I'm gonna mess it up. So starting with the equilibrium relationship, X, we have liquid mole fraction times, what was it? P dot, is it NRTL gamma? Gamma NRTL, yeah, this one. So again, we use the CHG tools version of our gamma function since it's optimized for Jax. We don't want the precision to kill us, so make sure it's fast, and we're also using the Jax version. It's optimized for Jax. And it takes a liquid mole fraction and temperature. You'll notice that this liquid mole fraction, might be curious where we're getting it from, and no, it should not be coming from our feed. Since stage 1 is quite a long ways from the feed, we should expect it to change. So actually, we need to make sure we're getting that from our liquid flow rates currently. So I don't know, mole frac for current stage, need for equilibrium relationship. So we have our liquid mole fraction, we know the flow rates, so it'll be liquid flow rate over the total liquid flow rate. And that should give us a molar fraction. So remember, these will be 2 values. We have 2 flow rates, so it'll calculate the liquid mole fraction. Or actually, I'm sorry, that's incorrect. It'll be 1 value because the liquid mole fraction is only doing it for... No, I'm misspeaking. I misspoke twice. So yeah, I was correct initially. So this is 2 values. Since liquid flow rates, there's 2 of them, and it will do it for the sum of both. So this liquid this liquid flow rate and this vapor flow rate correspond to 4 total, and each liquid flow rate is comprised of each component liquid flow rate. So there's 2 liquid flow rates from the current stage. There you go. So yeah, this will be 2 values, and then same thing with our vapor molar fraction. Do the same thing, but with the vapor molar streams or vapor flow rates. So NP sum V. Now we have the actual X liquid mole fraction, and I think we use the vapor. Yeah, we'll use it later right here. So we have our continuing our Raoult's law for non-ideality. Normally we have saturated vapor pressure. Is that just, I think it's VAP here. PVAP. There you go. And at a current temperature, which is the actual current temperature, not just some random temperature. It's from that unknown, that initial value or initial guess we gave it at that current stage for this temperature. And normally this is equal to our vapor fraction times our total pressure. So this total pressure is actually coming from that initial, not guesses, but the initial values we set at the start. So you notice that we want these to be equal, so we subtracted from the other side since we want them to go to 0. We're going to be solving for when they go to 0. That's that. Material balance, not as tricky, but we have to remember there's a liquid flow rate coming from the stage above. So let's start with that. Actually, let me just check this equilibrium, because now might be a good time to talk about, there we go, scaling. So there's this idea of scaling. We can actually deviate too far if our values, when they're not near 0, if they're not at a relative scaling near 1 is usually the standard. So these will all have different variations differing from, I guess 0 and 1. I don't know if that's the best way to explain it, but you notice that these are very big numbers and we want them to be equal to 0. Since you'll notice, well, they equal each other, so they'll equal 0, or not equal 0. They'll equal each other when they're, when it's like this, I guess is the best way to say it. But when we subtract them, in order for this relationship to be true, these both have to go to 0 for each component. I'm sorry, I misspoke there very badly. So that's for each component. So there's 2 values because there's 2 components in each liquid mole fraction and vapor mole fraction. So actually, we want both of these values to go to 0 is originally what I meant to say. So the idea here is we want to normalize this by dividing by a similar value. So we'll divide by the total pressure. And now these values will be closer to a magnitude of 1. So there's some reasons there. Honestly, off the top of my head, I'm not too sure, but I know for a fact that we can end up deviating a lot if we're further from a relative magnitude of near 1 or 0, since you can imagine for pascals, that's about the 100 of thousands. Enthalpies, about the same. Mass balances, not so much, but imagine how far off we get with round off errors and such when our values are not normalized. So that's the idea of dividing by a relative value that's similar of what we're actually solving for. So that'll happen with material balance and energy balance. Material balance will be dividing by the feed flow rate, and energy balance will be dividing by the feed enthalpy. So that's why those are defined there as well. Okay, so what was I saying? Liquid from the stage above. So I'll return mass balance for now. So, well, I'll just add this since I already explained that. So from the stage above, we have our liquid flow rate. Remember that we said it was constant molar overflow right here. So this is our definition of reflux ratio solving for that liquid flow rate. So we want that liquid flow rate, it will be R times D. But remember, for all of these flow rates we have so far, they have 2 of each flow rate because we're doing it for both components. So each of these flow rates should be in terms of the components. So this component value of the liquid coming down, well, it's the same as the vapor going up from stage 1 because it's all of that vapor had to be condensed and had to all come back down. Well, not all. The composition of that vapor had to be condensed. So that's why the composition is the same as what's coming down, since it's a total condenser. That is what I meant to say. So, yeah, vapor. So that's what's coming in. What else is coming in? The vapor coming up from the bottom. So while I'm saying that, I remember this liquid from the stage below, it doesn't actually affect our current stage. So I could actually just delete this, but I could just keep it at it as is. That's the same thing since I already copy pasted all of it. But again, this liquid from the stage below does not affect the current stage of stage 1, the topmost stage, or our unknown variables as we define it. Anyways, so those are the things coming in. We subtract the things coming out, so that is the vapor coming out from our current stage and the liquid coming out from our current stage. I'm going to copy that, but let's see what that looks like. So yeah, they're actually very close to 0. So let's see if I commented this out. How far would it be? Oh, actually not bad. So they are really close to 0. Very close to 0. But again, these values can be adjusted. Remember, it's not just this equation. It has to be all the equations that go to 0. So with that in mind, then we take the enthalpies of everything in our mass balance. So remember, I said it was feed enthalpy to normalize the energy balance, and this is, we take the enthalpies of each of them at their corresponding temperatures. So this is a liquid coming down is what we said. So P.HL, get the, you can't hear that. Yeah. My laptop likes to make very loud noises. Kind of scared of what'll happen when we use it during the final, but anyways, I digress. So remember, we have a number of moles, so that's our mole flow rate, and then we have a temperature we need. So that temperature is actually our reflux temperature, which I forgot to add up here. The reflux temperature is needed for our stage 1 because we use it down here to calculate the enthalpy of our liquid stream coming down. So that reflux temperature, again, it's the saturated liquid. It's the bubble pressure of that vapor coming up from the stage below with the perspective of the condenser. So stage 1. Stage 1's vapor composition. So what else? Yeah, we just keep going. P.HV, so that's a vapor enthalpy given a temperature of that vapor coming up from below. So we have to use a corresponding temperature. This is from the temperature of the stage below. Same idea for our current flow rates of our vapor and our liquid. So these will actually be at the same temperature since they're at the same stage. Again, these are from our initial guesses, so may or may not be correct. So let's take a look at that. Energy balance. Reflux T. Oh, yeah, I forgot to input it. So we'll just use it now since we're gonna need this later. So not bubble. Is it bubble? Saturated liquid first bubble. Yeah, it is bubble. NRTL. Plug in our vapor since it's a vapor composition going up from stage 1 into the condenser, and then we have a constant. I put pressure, it's temperature. Always do that. Then constant pressure, and we just grab the first value for that temperature. Yeah, pretty close to 0, not bad. Again, if I remove this, let's see. Yeah, we're about hundreds. So again, I guess equilibrium relationship is the one that strays off the most since those are partial pressures. So now we want to grab all of these values in an array, make sure they're in a JAX array. So JMP array. What am I doing? JMP concatenation, so it's all connected into one array. So mass balance, equilibrium, and energy balance. So all together to output all the values we've gotten before. So I could check this right now, but I have a feeling I could just wait and just look at all of them later on when I have all 3. So there'll be 3. You might be surprised since there's actually 10 stages, but we actually only need 3 functions. The first function being the first stage at the top, well, stage 1, and not really the first stage, but you get the point. Total condenser is its own stage since it only depends on itself and the stage above versus opposite of the stage 1, which depends on itself and the stage below. Now everything in between here is, well, just its own stage. We can have that as its own function since it actually requires all three vectors, and it actually won't have a reflux temperature either. So I think I'm just going to copy paste. You know what? I'll check it now. I'm feeling a little hesitant. Yeah, I'll check it now. All right, looks good. I don't know why I'm so hesitant. Anyway, I'll copy paste. So I'll call this just stage, I guess. No reflux temperature. We'll go pretty fast here. Vector 1. So we have to add that in. L1 of V1. And we split our vector 1 into 2. Vector 1 into 2. So we grab all the first 4 values, excluding the temperature. So it's 4 values instead of 5. Split into 2 once more. And we include our temperature 1. So that will be vect 1. Grab the last value to get the temperature. Looks good. Fractions still the same for the current stage, except we have to add in the feed. So the feed, I'm going to be using different, I don't know, variable names since we don't want them to get confused with what we're dividing by. So these are constant. These could technically change. Actually, is that true? We'll just be consistent. I don't think it's true since technically you could change them, but anyways. Okay, material balance. Liquid flow is not from the condenser anymore. It's actually the liquid flow from the stage above. So from the stage above. And we have a corresponding temperature 1 with that vector 1, the stage above. But we have to add in our feed. So feed is just its own flow rates. And the feed, our energy balance here is... No, you just add it in. We're saying we know those values. So we have to make sure right now feed total, yeah, so that's why they are different. So feed total is one number, but when we input the feed, that has to be 2 values. So that needs to be an array, or we could just multiply the total feed by a composition z. So we'll just use our feed composition there. Very good. Okay, 1 hour. Wow. Yeah. Do I want to check this? Yes, I do. Do it. Copy paste. We'll do this for the second stage. So right here, so technically second row, we'll do it. So 0, 1, and 2 for our unknown values. 0, 1, 2. So if we're looking at this stage, our current stage is index 1. Stage above is 0. Stage below is 2. So 0, 1, 2. Again, feed needs to be in terms of the composition. So 2 flow rates, we multiply by z. And I think we just call this feed h. So feed enthalpy actually stays the same. But anyway. Uh-oh. Oh, did I not shift enter? Wow, okay. Looks pretty familiar. I'm honestly pretty confident. I'll check it after the next one as well. So next one, last one, we'll call it stage N for the boiler. And I mentioned this before. It only depends on its current stage and the stage above. So no stage below. So no stage below. I copied this one, right? Yeah. And I can delete temperature 2. No stage below. Will fractions stay the same? Get rid of the feed. And no stage below. Equilibrium is the same. Get rid of the feed. Get rid of the stage below. No vapor coming up from the stage below. However, you'll notice that we can do an energy balance here, but it's actually not a complete, I don't know how to say this, since we kind of need to back substitute for finding the power of our reboiler, but we know it's a partial reboiler and it actually satisfies another mass balance. So instead of doing an energy balance, what's easier in this case is to satisfy the mass balance that the liquid going down must be equal to the boiler bottoms coming out and the vapor coming up. So yeah, yeah, let's do that. So, well, to normalize that, it's another mass balance. So I'll put that down here, fix that down there. And we'll divide by the total feed flow to normalize. So what did I say? There'll be a sum of all those values since we have the bottom's flow rate. So it would be the liquid flow, the sum of the liquid flow coming down minus the sum of the vapor flow coming up plus our bottom's flow rate. And yeah, let's try that. So yeah, stage M unknown. So stage above the last stage would be -2. And then the last stage would be -1, that entire row. And I think that's it. Oh, 1 exactly. Wow, okay. Alright. I'll go ahead and check these, make sure we're doing okay. Okay, good thing I caught myself, so I don't think it's been having any effect earlier on, but everything needs to be in terms of Jack's numpy. Because again, we're doing the Jacobian. Oh, sure that's the same. Yep. So the Jacobian, it's pretty picky, and there's some details there that I'm not even sure I'm aware of, but what is happening? We have to make sure everything is in terms of Jack's numpy so it doesn't yell at us. Oh, that's Jack's. Evaluate those again. Looks good. Jack's. An I spy here. Good thing I caught that. So right here, JNP. JNP. Not zeros. JNP. Okay. Wow. Good thing I caught that. So that would be pretty hard to find later on. We're still missing something. Okay. Yeah, I'm not quite sure I believe this value of 1 for the material balance. So go ahead and check that again. Okay, I think I found that one pretty quick. I don't know why I decided to add it, even though the liquid... So this liquid is actually analogous to the bottom's flow, so it should be subtracted from, since, again, our balance for this is essentially the liquid coming down is equal to the bottoms plus the vapor. So if we subtract both of them, it'll make it equal to 0. So both of these should be subtracted. Let's check that again. I actually don't believe that's 1. There you go. Something closer to 0. Very, very close to 0, in fact. Okay. I think we're good. We have all our stages defined. Now we can evaluate our equations. So our equations will need to be set up, I should say. So we have all our unknown values. We have all our, well, those unknown values are currently the initial guesses, but we have all our stages. We have the ways to solve all our equations. So now let's evaluate our equations based on our initial guesses. So to do that, what am I missing? I think I'm missing anything. Okay. So let's say, I don't know, ease, is that what we want to call it? So technically we'll have to modify this. So right now we're storing the equations as they are from our initial guesses. Next we'll do I don't know, not a reiteration, but it's the block tridiagonal matrix where we iterate it once, solving for our ease, or yeah, I guess technically solving for ease, but Well, the block triangle matrix, I'll go over it later when we actually do it. But remember, we have a diagonal of ones. We do a back substitution, and eventually we solve for the delta unknown. So that's the change of our unknowns that we have to move in, and that's another can of worms. So let's do it one step at a time. So we have our equations. There'll be another zeros. I feel like I can do zeros like of our unknowns since it does match the exact same, I don't know, shape. So let's look at that. So each stage has 5 equations, each giving their 5 values. So if we evaluate those values, it kind of it does take the same exact shape as the unknowns here. So that being said, yeah, I think we can just, I'm going to copy all of these since we'll need them. So that we need, I have to remember to change this. I always forget this one. And this one. So you might be wondering, why am I copy pasting all of these? It's because you're going to be using them. So one of these is going to be a loop of all the stages. This is going to be hard coded. This could be hard coded. So this is the first row. So we'll be able to actually look at this. So the first row is, am I doing this correctly? These are these the Jacobians? No, these are equations. I don't. I'm mixing things up, which is not good. So yeah, we hard code the first row of our equations with the first stage. So just like that. Yeah. Yeah. Look at it. Now this should be occupied in the first row. Beautiful. And it should be the exact same values as what we got here. Perfect. Next up, a little complicated, but not too complicated. We got our for loop. So we need to change all of these to, well, I'm cheating since I know it, but we have for I in range. So what is our range? We start from 1, so index 0 is done, 1 to the very bottom, right before the end. So we can say something like from 1 to ns minus 1, number of stages minus 1. So that would go to 0 to 9. It doesn't do 9, so it does 8. So colon, and now we have to differentiate between the feeds. So to do that, we have if I, the number of iterations or the indexing, is currently equal to the feed stage, we say it is at the feed. So, well, current stage. So stage above would be I minus 1. Current stage would be I. And the last, well, stage below is I plus 1. And this stays the same. Then, if it's not, well, we actually need to store that. So equation at the current I, whatever it is. So it'll be down here, I think 8. Or yeah, 8 is where our feed stage is. So at index 8, second to last. I'll actually stop at 7. So go to 6. But anyway, so if it's not at the feed stage, we do the same exact thing except remove the feed and feed enthalpy. That's why I included it earlier. Now we can remove it. Well, actually, we still need them, but at 0. So not technically remove, but they are 0 if they're not at the feed. There we go. So let's see those. If that populated correctly, we should see everything until 7. So this is 8. Is it 8 or 9? So 9. I do that right? 1, 2. Oh, actually, it doesn't ignore. It does go to the last stage. What am I saying? So it'd be number of stages. 10 minus 1 is 9. So it goes to 9. 1, 2. Well, this is 9. Stops at 9. That does ignore it. I'm going crazy. But yeah, it stops at 9. I'm confusing myself so much. So this is 10. We have 0 done. We have 1 through 8 done. So it does ignore the last stage. Okay. Or this index here. So that's exactly what we want since this is right here. So the last stage, -1. And it's equal to the exact same thing. Now we will populate the last row. Absolutely beautiful. So Pretty sure I checked it already. I'll check it again real quick, but I want to remember, make a note to myself that eventually these will be functions that we'll evaluate. So I'm going to have a function that evaluates the equations here, like that, and it takes in an unknown as a parameter. Because the reason why we're doing this is because we have to reiterate these equations over and over again, so we can find at the very end of the day the absolute value, the norm of our equations. So minimize that sum square error is our end goal. So I have another function that's going to be the norm. And it also takes in the same unknown. So we're going to be trying to minimize that. Of course, we return back our equations. Okay. So getting a little ahead of myself there, but just so I don't get lost, I have those noted out. But watch me forget anyway. So let me pause again. I'll look at this real quick too. Okay, no hiccups yet. Perfect. Okay, next is probably, it's something we've done before, but it might be a little complicated to comprehend at the start. So we've actually, what's the best way I want to do this? So let's that and this, but trying to find the block tridiagonal. Here we go. And we can do a main screen here. Why not? So actually, I want to swap these. So let me switch back. Oh wow, iPad's still open. Awesome. So something like that. So I have the tridiagonal matrix open. So we have what it looks like. I'm going to be referencing it a lot, but actually this might be a good point to switch back to the iPad just to kind of draw out what it looks like, kind of get an idea of what we're doing here. So yeah, this is definitely going to be a 2-hour video. Yeah, let's go back. And boom. Okay. So I'm tempted if I want to look at my notes for the drawings. This is technically not on the assignment, but anyway. The basic idea we have, oh, come on now. Actually, I could just look at the previous video. I don't know what I'm talking about. This has always been free. So, we've done this before, block tridiagonal, but again, starting back here, we have our idea of the Jacobian, again, the multi-dimensional equivalent of the derivative. So we have to track how far we change. Again, this will be our delta V in our case. So I think that's the only main change here. And then our functions now depend on more values than just x. So kind of to write off to the side here, our functions, we have, well, 5 equations. So it would be something like f1 is dependent on not necessarily all those 5 values, but it could be. So some cases it could be, some cases it doesn't. So remember all our equations, we have material balance, 2 of those, equilibrium balance, or not equilibrium balance, but equilibrium relationship, we have 2 of those, and 1 energy balance. So for our mass balances here, I'll just say they're the first 2. Technically, it's just the flow rates that we're caring about, so that would just be the first 4. So something like this. First 4 unknown values. And then for our equilibrium relationship, what does that depend on? Those are from our liquid mole fractions, so technically those also have dependence on our flow rates. So I guess it also all before. So you get the idea. For a general case, it could be all of them, it could be none, it could be 1, etc. So don't want to get too complicated here. And then I also mentioned this vector of unknowns. So we have vector, but we have a change in vector. So change in vector is equal to, well, it's a change. So our vector at the next position minus our vector at the current position. It tells us how much we need to change. And then for a vector, can you see this? Okay. For a vector array, that is our list of unknowns. So we want to say we had x, y, z, omega as our unknowns there. So that's all that's changing, honestly. And then with our Jacobian, that'll be a little bit different since we have more variables here. So if our Jacobian It'd probably be something more like partial derivative. So remember, Jacobian tells us the sensitivity of each equation to each unknown. So we take the partial derivative with respect to every unknown. So x, then y. Hopefully you get the point here, but I'll just do it all for the first row. Z, and I think I had omega as well. And we do this for every equation. So you imagine how big this Jacobian kind of gets. If we had 5 equations and 5 unknowns, and for some reason I only drew 4, so you imagine this would go up to 5 columns and then 5 rows. So 5 equations going down and 5 values going across. So this would be a 5 by 5. So that changes what our dimensions kind of look like here if we have 5 by 5s in here for every single point of our matrix. So I kind of tried to draw this out in a copy paste style. So this is actually what we're solving for, and then this is our delta unknowns. And it may help to think of it logically. I don't know if that might help, but we have it's 10 by 10 for stages, and then each stage has 5 layers. So layers is what they use to denote that third dimension. At least that's what I found online to teach myself. But we have rows, columns, and layers. So we have a number of layers to each kind of value, which we normally wouldn't have before. So this is actually 100. I just realized that's kind of insane. So 100 and then 5, so 500 values. Pretty insane. But remember, most of these are zeros because we have neighboring dependencies for each stage. We only care about the stage above and the stage below. And then we have the special cases for our topmost stage and bottommost stage. It just be bottommost stage is these two. What happened? And topmost stage is these two. The rest are zeros because they don't depend on stages that are not adjacent to them. And again, for our, well, there's a negative sign, very important, but for our delta V, so this is our delta vector, and these are our equations. So we actually have our equations. Now we need to solve this block tridiagonal matrix with our initial guesses for those equations and solve for this delta vector. So that's what we'll need to do here. And to do that, I might need to go back to that previous video. Remember, we had to, is all focusing on getting our B's, I'm sorry, yeah, all of our B's into ones and all our A's into zeros. So to do that, starting from the top, we had to divide across the entire row by B and then subtract from the next row. So by doing that, well, we also had to multiply by A2 as well. So I think I had this numbered out here. So first step was divide by B1. Second step was multiply by A of the next iteration or next row, next stage in our case. And then the last step was to subtract 2 minus 1. So then you'd have a B minus here. And we call that our B star. And remember, the key part here is that we only store our C modified values, since across the diagonal here, these will all be ones. So these C modified values is what we're looking at. And did I have that as a C star anywhere? Of course I didn't. So that's actually right here. So we have the ones, and then we have the modified C values. As you can see, kind of becomes an abomination with the number of B's, but remember, this is pretty fast for GPUs or for computers in general. But remember, this only applies to very small scale problems, since at the end of the day, we will have to do a inverse, which is normally avoided in linear algebra. So by doing this, this approach, we can solve for the last unknown and use a sort of back substitution. I went through this example in a previous video. But again, I'll be referencing that line of code as well. So I think that's enough refresher. I think we can just go into this. The main differences, instead of dividing by a B modified star, we have to remember we have to multiply by the inverse. So that's the main thing. And then kind of treating everything as a matrix is the biggest part here. So what's the best way to do it? New main screen. We have the full view on the left and the copied. Well, I'm going to be referencing it mostly. Kind of copying pretty much too, but it's my work, so why not? Okay, what are we doing? 1 hour 20. Okay, let's do it. So we need to define our C modified values. So I'll just do capital C to denote matrices. How about that? I think up here. Oh my goodness. Yeah, this is gonna be a long video. Okay. Yeah, defining our C's, we have, this is gonna be a 3D matrix. Remember, it was our giant Jacobian and then 5x5s. However, if it's just the C's, we only have 9 values. Remember, the C's stop at a diagonal and it's less than the number of B's we have, one less. So it actually doesn't appear in the last row. That's the whole idea for the back substitution. So we only have 9 C's we care about, and all of those will be 5x5 since they're all Jacobians. So, well, I also need the Jacobians, so we'll do that as well. Okay, so it is a NP array of zeros, and we have 10 rows, and we have, do I need, I think I need double, okay. 10 rows, 2 times NC plus 1, so 5, 5x5? Actually, I don't think I drew my thing right. Because it would be 10 stages, or 10 stages, 5 columns. No, I think it is 10 stages. Yeah, anyways. So we have 10 stages, but each of them are 5x5s. Oh, I'm not trying to do the Jacobian, the big 10 by 10 by 5 thing. I'm just doing the C's. So anyways, this will be each of the C's. So we have to record all of the C's in one array. And remember, one C is a 5x5. So we have 10 5x5. So that's exactly what we're doing here. It gets confusing, you know, at 2 a.m. So yeah, let's look at that. I think we can call it modified values. So we're going to be storing the modified values. So C's mod, or let's just do C mod. Okay, just big C. So this will be 5x5s. And should be 10 of them. But of course we index 0 to 9. So let's do, we'll do size, let's do shape. 10 by 5x5. Beautiful. Okay. I don't think I need to see it, but we can look at it every now and then. So yeah, now we need the Jacobians, so we can do that right here. Does it need to be a 4? I might just, I want to leave it. Yeah, I might just copy paste everything. So I mean, yeah, we're not gonna run it all at once. The goal is just to see how we're going at each step. So I'll copy paste it and add, so we don't move things around. We can still see previous values we evaluated. So yeah, let's do the Jacobians here. So the Jacobians, we have stage 1 Jacobian. Now I'm actually going to add the just-in-time thing now. So the Jack's JIT. So this makes the operation faster. Don't ask me how, I don't know, but since it does take quite a bit of time once we start iterating our last loop through, so we get a, make our equations all go to 0 and take a step for our delta unknowns in the certain direction. So more on that later. So we want the Jack's Jacobian of stage 1. And remember, stage 1 takes, do I actually need to be full screen here? I don't think so, but anyway. Stage 1 has inputs, or are we, of 3 parameters, but we only want to take partial derivatives of the first 2. So that'd be 0 and 1. First stage, for all the stages, we only want the first 3, so 0, 1, 2. We don't take partial derivatives for the enthalpies. And then for the last stage, stage n, we only have first 2. So we index that accordingly. So it would be 0, 1 for our stage 1 Jacobian, and you'll notice that this should be, when I evaluate it, it'd be giving me two arrays, two 5x5 specifically, because that would be our B and C, if you remember from our, let's see here. From what our, oh, that's my answer. Jacobian, my notes. No, the last video, here we go. Green. And yeah, this is our B and C right there. So that's exactly what we're doing for the first row. These are 5x5s. They are the Jacobians. Again, the sensitivities of each equation for each value. So I want to evaluate this. Where it's right here. So that stage 1. Badoom. Please work. Wow. Beautiful. So you'll notice it is the 5x5. Yeah. I just can't count. It looks way bigger. But anyways, this is a 5x5 and this is a 5x5. So they took the, essentially automated the partial differentiation. So it's automatic differentiation. That's what the Jacobian is. Or the partial derivatives of each equation for each unknown. So notice that there's a bunch of zeros here. Again, not every equation takes every value or is dependent on them. So that's why most of these, isn't most? A decent amount will return 0. And you'll see that more for the other stages as we store them for our C's. So yeah, that's the best way. Yeah, I think we get the idea here. So let me do this and open up back and main screen. So we could do full collab for now, since it'll be a little bit. So we want all the Jacobians. I'll do them all right now. So I'm definitely one to forget. So it's a little dangerous copy pasting, but you just have to remember all the things that change. So for the stages, we have dependencies on stage above, current stage, and stage below. So that's why we have 3 parameters and we index them as 0, 1, 2, since we have 3 parameters ascending in order. So the first parameter, second parameter, third parameter, and we had feed and feed enthalpy, but we don't care about that. Stage N is the last one, so we need to make sure this is stage and this is stage N, and it also has only 2 parameters that we care about, so indexing is at 0, 1, just the same as stage 1. Shift enter, make sure that's evaluated, and I don't think we need this anymore. Right? Yeah. Okay, now, I mean, that wasn't that, it was pretty quick. So anyways, we can do this and this. Here we go. So now we have values for the Jacobians that we can evaluate them at. So how do we want to do this? I need to get the B and C values. So here we already had the values for B and C. So here we're dividing C by B to get our modified C value, the first value at that. But in our case, these two are matrices. So we actually need to unpack them from our Jacobians, which are the partial derivatives. So I will do something like B comma C unpacking the Jack's Jacobian. So stage 1 Jack. Actually, I don't know why I deleted. Is it still here? Whatever. It was right here. So copy and paste. So these were our 2 arrays, if you remember. So now we have the B and C values. So if I do something like BC, show up. Go. 2 arrays, 2 matrices, 2 5x5s. So let's get rid of that. Now we do the same thing as what we do here. So we have to, for the first values, we have to divide, well, the first row, remember the first step is divide by B. So our B isn't modified yet, it's just its normal B. So dividing by B, we have C mod big C. We store the first value, so 0, and following our template here, it is our C. Hold on a second. Am I confusing something? Oh yeah, we have our C. What am I doing? So C, yeah, I know what step I'm missing now. So it'd be C over B normally, right? But remember, these are matrices, so we have to take the inverse. So something like B inverse is the JNP linear algebra inverse of B. So now we do B inverse matrix multiply at C, because that's the same thing. That's the matrix equivalent of dividing. So next up is our E modified values, but it's a little different since we're starting with our E's here and we just modify them within the same array versus we had two separate arrays for our modified E values. Remember that these are two different arrays. We had random integers generated for this at the very top of this line of code. And then we had array of zeros generated for our modified E values, so our equations. But in our case, we just solve for them from our initial guesses, and we're going to modify them in our exact same array. So that's the only difference there. Call them E's, right? Yeah, E's. So equations at 0. So that first row, we want to divide that first row currently. So we're kind of rewriting and divide it by B. So that would be B inverse matrix multiply. Same thing as division. So note that these are actually the more simple ones. We don't have a modified B value yet, but you can imagine where it gets a bit complicated down here with the modified values. Shift enter. Let's take a look. So C modified should give us a, oh, is that the right one? Yeah. Whoa, what happened here? Do I need a full screen? Probably. There you go. So now the first set of values for these technically 10 5x5s are now filled up. So we're going to end up filling all of these values. So notice that some of these are zeros. Again, that has to do with dependencies. And well, we had a matrix multiplication of our inverse. So I think it goes like that for all of them. But anyways, yeah, let's keep going. And then we can look at our E's as well. So these E's now should be different from the ones earlier, at least for the first row. So look at these values, 1.409, completely different from the first row. But everything else should be the same since we didn't touch them. So we'll keep going like that. Hopefully I shouldn't need to keep checking, but we can. The next one will be a loop, so that'll be more fun, I guess. So, doing that. Main screen. A little bit more complicated, but shouldn't be too bad. Yeah, we can keep it in the same cell here. So honestly, let's copy paste it. Now we're iterating for all the stages in between after the first row since they're pretty identical, but the key here is we have to unpack them differently since this is a matrix where one of them will have a feed, one of them won't have a feed. And that's when we plug in our Jacobian when we have to substitute in values there. So first off, let's change this since it's not just n, it's number of stages, -1. So that goes to everything but the last stage. So it'd be 10 minus 1 to 9, and it doesn't cover 9. So it only goes to 8, index 8. Yeah, let's just comment this out for now. We have to do a similar thing up here. I might just copy this. Yeah, I could have just copied this whole thing, honestly. Did I copy the for loop too? Okay, no, just the conditional. So this is correct if I'm at a current stage for our loop. If that current stage is our feed stage, we want to apply the Jacobian. So Jacobian, so that's just Jac and Jac of our inputs. And this is correct. Stages are correct. Indexing is correct. And then it is E. Is it the same thing? Or no, we are unpacking those values. So these will, for the Jacobian, will be outputting 3 arrays. So let's just look at that, honestly. We could do 0, 1, 2. Why not? I think I'm muting myself and unmuting myself. Okay, we're fine. Yeah, tilde is my mute button for whatever reason. So that should be good. And this should be 3 5x5s. Beautiful. 3 arrays, 3 5x5s. Again, notice the number of zeros. And that will only continue growing, at least within the bigger array, as we continue down this loop. So we'll unpack this as A, B, and C. So can I delete you, pretty please? Okay. So that's what we want to do. We don't want to store that value. Versus a different array would happen, of course, if we don't have these enthalpies in the feed flow. So that's why the values of A, B, and C will be different depending on if it's at the feed or not. A, B, C. Oh boy, 140. All right. Yeah. And now I think this is done, right? So again, we had to take the Jacobian since this is a matrix instead of, we already had values here. So it was originally just values across. Now those values turned into 5x5, hence the name block tridiagonal. So do I want to keep this? I'll keep it up here. Why not? Now, I think most of these are pretty similar. So let's start with our modified values. So similar to up here, we have to take it inverse again since we're going to be dividing. As you can see, we divide by the modified value. So we can actually combine the modified value and the inverse step into one. So that would be modified inverse. How about that? And honestly, I don't think I need this anymore except for these two, which I might just copy paste so I don't have to keep looking back. And I'll explain them as we go. So that should be good. Yeah, let's just stick with it here. I don't know why I needed the split anyway. Okay. So I guess it's worth labeling. So hard code first row maybe. And then loop middle stages. And then that's where we're at right now. So I said I was going to combine the modified values and the inverse into one step. So what I meant, we'll do inverse once more, then an algebra inverse of, so it's our B modified. So this is our B modified. We have to turn this in terms of matrices. We already unpacked our B. We subtract the A and we matrix multiply by the C. But this C is from our list of C's that we modified previously. So what do we call that? C mod. C modified. And then we, instead of I minus 1, oh yeah, it is I minus 1 since we're still in a loop. Okay. Indexing, I always get those mixed up if we're in a loop, and then I'll end up writing I when we're out of a loop or some value when we're in a loop. So this should be pretty good. And then next up, we have the C modified values. C modified values in the loop for that current index. That is simply our B modified inverse matrix multiply our current C. So is it worth explaining where this comes from? I feel like I already kind of explained it. I can explain it once we do this. So yeah, let's finish this for this row. So E modified, what is it? Just E's, right? That's what we called it. At the current index as equal to matrix multiply inverse. So get rid of that divide. Well, that's the equivalent of dividing in for matrices. Matrix multiply, and then parentheses, we have our E at the current index minus A at the current index, which was unpacked previously, and it will change depending if we have our feed, if we're at our feed stage or not, and then matrix multiply E at the previous stage. Shift enter. Shift enter. Look at that. How are we looking? Oh, well. Oh no, yeah. I was like, that last row should not be populated, but no, it's the same. Again, I forgot we're doing it within the same array. I was playing around earlier and tried to do it within 2 different arrays so we could compare it a little better, but it gets a little messy since you have to keep track of what array is going to where. So I just got to stick with what we did in class, keep it simple. So I think I said I was going to explain that. Right? So that's the best way. Do I need to split it? Yeah, I don't need iPad, so let's do split. Where are you? Here. Okay, so where is this? Yeah, right here. Yeah. So again, I mentioned the first row was pretty simple. You're just dividing by B, but then once you get into the middle rows, it gets a little hairy. So what happens is that you have to multiply the previous iteration by A. So if you follow the steps down here, did I even do it down here? A little hard to see. Oh, you can't see my cursor. So after 2, so 2 is denoting the second row. So again, we still divide by B, but now B is a modified value. Since earlier we had to subtract 2 minus 1, stage 2 minus 1, you get that modified B value here. So this modified B value coincides with the B inverse. What we got here, we take the inverse again since we have to divide. We can't just normally divide with matrices, so you have to multiply by the inverse. So this is our modified value of B. And then to get our C, this C value, we divide by B. So we divided by this B modified value. And then for E, it's a little different since remember C doesn't change since it's a 0. You're subtracting a 0 from the previous row. But with the equation side, you have to subtract from the previous equation, which was modified. So the reason being there, so instead of just a simple divide by B, now you have to subtract and then divide by B. So it was E2 minus A of the current stage times the previous iteration of E. So that's why it's previous iteration here. Yeah, if it's still confusing, I definitely recommend watching this video again, where I went over this. I think this was, what was the name? Like Newton's method and such, Thomas algorithm. So I go into a lot more detail there. I'm afraid I don't think I can do it right now off the top of my head since my focus is on getting this thing correct on this mesh calculations, but yeah, definitely recommend checking that out if it's still confusing. So I think we're done with that. Let's focus on our code here. So we're almost there. We have to get our bottom row now. So with our bottom row, we have this line of code. So I'm actually just gonna yoink that up. Can I just do this? Yeah, I'll cut it and paste it since eventually this will all be one nice gigantic cell. So it'll be a hard code last row. So the last row, remember, it was just A and B. So we unpack that. The best way to do this. So we have on a loop. So A and B, we unplug that from our, so these are matrices. We get them from our JITted Jacobians. So just-in-time operation is what it stands for. So let's see, stage and Jacobian, and then we evaluate it at the last values. I did that earlier right here, just so I don't have to worry about it anymore. Right? Okay. Yeah. So now we have our A and B values. And now we get our B modified. So it'll be B modified inverse again. So I think I can just copy paste this, but I do have to be careful. The indexing is not at I this time. It is at, so I can think about this. So originally the modified is at n minus 2. The inverse, if you want to take the inverse, you would have to take the C mod from the previous. So that would be the same thing. It'd be ns minus 2. So 2. So again, there's no C in this last row, so we have to look at the C above. And remember, indexing stops. So in our case, it's 10 stages, 0 to 9. So 9 would be the last stage, or last row, which is the last stage. So that would be ns minus 1 as the last stage. If we want to go to the previous version of C, because there's no C at the current row, it'd be ns minus 1 minus 1, so minus 2. Yeah. Yeah, looks good. Last thing here. We're going to do this. So yeah, ease equations at the last row, because equations still exist at the last row. We want to get that. And yeah, I'm just having a brain fart. So you do have to, yeah, I was expecting to do a C mod here, but instead it's just this. So can I just copy paste this? Except I will have to change the indexing, which is a little tricky here. So inverse there is good. We divided by B. Inside the parentheses, we have n minus 1. So instead of n minus 1, it'd be the last row, which is ns minus 1. A is the same. We unpacked that earlier. Matrix multiply E from the previous iteration. So the last stage, the stage above, which would be ns minus 2. And let's take a look. No, C shouldn't have changed. I know I haven't been looking at C, but it should be fully populated by now. And now this is how far we are. Wow, that is very different from what I was expecting. Every time something is slightly different. But anyways, let's see. So now the last row has changed as well. So these are our current values for our equations, and you notice that they are not at 0. And we want them at 0. So looking at the deviations, it's pretty different across them. So let me just check this real quick, see if I'm on the right track, and then we'll get started for our delta unknowns right here. So, yep. All right, so I think I found the error here. So this reflux temperature, we grab that. So knowing that our condenser is at a saturated liquid, it's a total condenser. All the vapor going up is completely saturated liquid. We're finding that first bubble. What I didn't account for is the fact that we have to unpack that from the current and flow rates. So I can just copy paste it. Yeah, why not? So I will have to take out what we don't need. So we want the current Y unpacked outside from this stage 1 so that we can use it as a reflux temperature. Yeah. What am I looking for? Paper. Let's try that. Shift all. This will be wrong. There we go. They're still pretty big. Yeah, I'll check it once again. Okay. I think this is as close as it's gonna get. Really, these don't really matter. As long as we're not too far from 0, it should still be able to converge. But the only other thing I changed was this. So I said I was gonna make it true. Remember, in the original function, this was a vector right here. I need to make sure that was also unknown. So that was the first change I made. Make sure we're grabbing it from the first set of unknowns, wherever. Did I even show that? So the first set of unknowns, we grab the liquid and vapor flow rates. Specifically grabbing the vapor flow rate so we can find a vapor mole fraction. Where are we? And we use that vapor mole fraction from the first stage as a guess for our reflux temperature. So that was the first guess. I know a lot of my mistakes in the past were the indexing here, so I checked all of those. Those are pretty good. So whenever you're in a loop, make sure you're indexing, you're actually using the loop. I know normally copy pasting, it's probably hard to find that, so I'm still within a loop here, still a loop, but then I'm outside a loop here and down here. So let's just keep on going. Last step here is the delta x's. So, yeah, let's make it its own cell for now. Eventually we'll need to combine it, but so we'll change this into a set of, let's just do it below. So it would be, let's zoom in. Delta x unknowns, or well, just delta unknowns. This will be zeros like, what do you want this to be? So these are unknowns. We can just make it like our unknowns. So it will be our 10 by 5 again. Yep, and we'll fill that out accordingly. We have this index -1, so we've actually solved for everything. Remember the last row, we solved for everything. That all we had to do is set them equal to each other and then some backward substitution. So that's what this is doing. We're starting at the second to last row, going up and stopping right before, well, we stop at the first row, right? This include this last index, so we would be ending at 0 actually. And then -1, so we take a step backwards. So I think I can just copy this, put ns, number of stages, instead of n, and then didn't even finish out the last line. So it was ease at the last index. So setting the last unknown equal to the last equation, because everything has been zeroed out. They are equal to each other. And we go backwards, and I think I just copy paste this. So this is delta unknowns. We're in a loop, so we index with I. So at the current index, we have our E modified. That's our E's, and this is our C mod. Perfect, and matrix multiply. So that comes from when I did my example here on the right. We kind of derived that expression. What is happening? Can we do main screen? Oh, it's yelling at me. Right here, after we set them equal to each other, right here, so it's equal to the modified version, the delta unknown, we have our expression. Remember, this comes from this grouping up with the current stage, the next one grouping up with the last stage. So going down, we have current stage x2 is just 1, and then c2 star. So this 3 is actually a star modified value, and it's multiplied, and we're saying that's equal to the modified e2 value down here, and we isolate for the current x. So everything's moved across. You have e minus the c star of the current stage times the x at the previous stage. Well, I guess the stage below. So stage below, everything should be correct here. And this is instead of x, it's delta unknown. Looks good. See what that looks like. And yeah, let's look at delta unknowns. Oh, this looks decent. So these are the steps we need to take to go to 0, or our equations to go to 0. So we're in a hyperplane. Do I have that pulled up? I think this concept of a hyperplane was in class. So this is 2D and this is 3-dimensional. So hyperplane, thinking of multi-dimensional. If again, we approximate this as a line. So this is kind of what it looks like from the side. This delta unknown is telling us how far in what directions do we have to move in to make sure that our equations for, so our e's, those arrays of equations, those values go to 0. So there's a range of values we can go to, and instead of going towards, so I guess it might be helpful to write it out. So it would be something like unknown plus the delta unknown would help us reach 0. But there's something wrong with this, and the problem is that if we go the complete benchmark all the way, if we add that to our current unknowns, since it's saying that's how much we need to add so that we get to 0, this actually is inaccurate, because this delta unknown is only accurate within the bounds or the near vicinities of our guesses. So the idea is we're going to have some multiplicative factor t is what we use in class. So it's going to be any variable name. And this multiplicative factor is we're going to end up going very small steps at a time, either up or down towards these directions, such that our unknown, this value, this norm or sum square error is below a certain tolerance. So we're going to minimize this multiplicative factor. And remember, I was talking about the norm earlier. It's this exact function. We're going to be evaluating our equations once more at our new guesses and then getting the norm of those. And until we hit a certain tolerance, we'll keep doing all of this over and over again until we get a decent guess, until all our equations go to 0 and that tolerance is below that threshold. So the actual value. So what happened here? We don't need this anymore. Happening. Okay. So let me look at this real quick before I do anything, since I can't remember 50 numbers. So let's see if we're on the right track. Okay, I think we're doing fine. So let's start with do we want to minimize it first? I think it might help to start with what we're actually looking at. So let me copy paste this. Did I merge these yet? So let me merge this. Yeah, I said I was gonna copy everything so we could see everything. Sure. Let's do this. So want to, right, every time we evaluate our equations, we do this all over again and we return our equations once more. And we get the norm of those equations. And that is, we return the sum. So we want to do JNP sum. Sure. JNP sum, what is it? Not sum. It's a linear algebra norm. So norm or absolute value of all those vectors. Well, that means a lot of dimensions, more than 2. So I guess just think of it as absolute value. So that's sum square error. Yeah, of this evaluation eval equations given that unknown. That works. And eventually, so I said I was going to find the sum square error of this. So the idea is we have the norm evaluated of these values. So this unknown is changing by how much we're walking across or adding to our unknown from our delta unknown. So this is the direction. We're moving in small steps of t, and we're either adding, and I think we'll end up subtracting is what we'll find, to our unknown. So bits and pieces at a small time instead of going all at once, since going all at once may be incorrect, which is definitely what we'll see. So it's actually a norm. What happened? Norm evaluation of our equations with this changing delta t. And what we can do is to find this delta t, we can do an anonymous function, lambda t, and minimize this function for t. So to do that, I can just take this. So it would be minimize scalar. That's one of the functions I talked about at the very beginning that I said I would use near the end. So we are actually nearing the end, believe it or not, at this 2-hour benchmark. So minimize scalar takes in a function and a bracket. So bracket is another function we'll need. It takes in a function and it'll output the points of a bracket where that minimum will be contained in. And that minimum is what minimize scalar needs. So that bracket contains a minimum that minimize scalar will use to find the minimum value of t, since it's now bracketed. Same way we use root scalar and bracket with that secant method. Oh, where are we? So here. I think I copied it, right? Scalar, and then copy, and I need a bracket here. So our bracket, so this gets a little annoying sometimes because it makes it want to run again. It says the tuple isn't iterable or isn't callable. No idea why, but running it all fixes it. So I might end up having to comment this out when I have to run this all. So just a forewarning. It's our function, so bracket our function. And then I don't think it needs anything else, right? Yeah, it's gonna output that, and these are all default. Function takes in a bracket. So let's see if this actually gives us something. Bracket. Please work. Oh no, I didn't get to see it. Now it's gonna yell at me for this. Yeah. Let's look at it first. Then I'll store it, and then I have to look at it. Oh, it's so annoying. Let's see. It's worth it. This might be a while though. Is it worth trying to combine everything at the bottom while we're waiting? It might be, since yeah, unless it finds an error. So hopefully it doesn't. Okay, cool. So we found our bracketed. Yeah, it's gonna have errors. Because I didn't store the bracket information yet. So we're looking at the first three outputted values. Those are our bracketed values, the final points of the bracket from our bracket function. And the bracket goes into our minimized scalar, where the bracket only needs to satisfy that xa, xb, xc, which is exactly those values, those floating point numbers that contain the minimum value. So it's a triple tuple, however you want to say it. So we'll need to grab only these three values. So I do bracket is equal to that. Yeah, I don't think I can keep this up, so I'll just set it equal how I had it before. You won't be able to see this, but remember, we're only grabbing these three values here. So it would be the famous emoji face. So everything except 3. And yeah, we'll need to store this again, so I'll have to run it all again. But just so you can see what the actual result is before I store it, I'll run it. So this will output us our actual value of t, that multiplicative factor that we want. I think x is the solution. Yeah, x is the attribute solution array. So, yeah, we can get started, I think. So I'll have to copy paste this, essentially. Down here. So now we can actually do our for loop once. Oh, there you go. I won't get ahead of myself. So this is the actual value. Notice it's negative. So we actually walked backwards a little bit from, well, I guess most of these are negative. So I don't know. Some of them went forward, some of them went backward. But again, it was only about a 1.01 multiplicative factor. So not that too much of a difference between adding our entire unknown. So, well, it is a difference. You multiply negative, but anyways. We want to store that value, so we do something like t is equal to dot x attribute. Similar to how we did root, we store it as res, then we did res.x or res.root, etc. So I don't think this will, it might yell at me for this. Okay, if it didn't yell at me there, it's definitely gonna yell at me in this big loop that we're about to do. So I will copy paste our block tridiagonal. And I didn't include the x's. What am I doing? The delta unknowns. So I'm kind of going backwards here. So let's start at the top. So we're going to be running a loop for some range. Let's say, I think in class we do 1 to 25. Okay, yeah, we're almost there. 1 to 25, and we want to evaluate. So we grab our equations from our evaluating equations from our unknown currently, and we have to make sure that unknown is changing all the way at the bottom. We'll also have minimized bracket, so I need to put bracket and minimize scalar. And then we have our update. So that would be unknown. And we have that up here. Right here. So we're updating it by moving across however many steps based on our multiplicative factor. And then we actually have our minimum here. So yeah, I know I'm kind of all over the place right now, but bear with me as I'll explain this. So I'm just trying to group everything so I have everything I need. So go, and then we have our delta unknown here. Then there we go. So at the very start, we're iterating all of this over and over again so that we can get an updated, accurate value of unknown, where the norm will fall below a certain range, and will also, I'm missing some indents, but I'll fix that as well. So we have our equations, and now we have to get the norm of those equations. So it was norm evaluation, right, of that same unknown. And this is a scalar value. So notice that this all of these, this entire system essentially boils down to this norm being less than a tolerance. So that's exactly what we need. If this norm is less than some tolerance, I think we use 1e to the -8th in class, and we break out of this loop. And if not, we continue it. So let's print out how many iterations we're doing. So we do print I and our norm. See if we're going down. Yeah, so what I was saying about this entire thing being a scalar, so all these unknowns, all this evaluation of equations going to 0, that 10 by 5, those 50 unknowns get sum squared errored, but you take the norm of those values, so you square them and add them all up, and you have one single value that you're comparing to 1e to the -8th. And if that is close enough, well, obviously this is near 0, but we want it to be below this certain tolerance, then we have our solution. So we keep repeating this unknown. We updated it based on our new bracketed guesses from our delta unknowns, since this is based off the previous iteration starting from our initial guesses. So this is our block tridiagonal. Let's make this into within our loop right there. I guess we can label it something like block tridiagonal. Sure. And then we have our delta unknowns and our brackets. So this needs to be within the loop as well. So let's see if this works. Praying I didn't make a mistake. Oh, yep. So that's what I was saying earlier. The tuple doesn't like to be called. So figured just needs to run all. That's usually the best cure. Don't ask me why. There we go. After this, we're just graphing if this works. So let's pray that this iterates correctly. I think in class it took about 4 iterations. Mine usually averaged to 5. I've had one take 7 and still work. So it's hard to see where all the changes come from. So, oh boy, start with 2. We're hoping we're getting into the negatives. So scientific notation. Oh boy, what? Not iterable? Yeah, I don't know what is up with this thing. It just doesn't want to be iterated. So I don't have it anywhere else. And I'm assuming there's probably, I don't know, I could just run it all again. Like, I'm not too sure where the error comes from, but you did notice it was getting smaller. So it was like 2.3 to like 0.1. That's exactly what you want. The tolerance is getting, or the norm is getting smaller. So the iterations keep progressing. It's probably gonna yell at me again. Yeah, I might just pause it and see what happened. A moment of truth, honestly. 2 hours, yeah. Does not want to be called. Okay, so I suspect there is something else holding this back. Can't remember exactly what I did last time when this happened. So, yeah, I'll try to find the error here. Usually running all works, but fortunately it did not help the second time. So let's look there. Okay, it's working, and it's actually giving the same values as we got in class. I literally only changed the name of the bracket and added the default values, but it looks like it works if we do it that way. So that's pretty nice. And I think we're actually going to converge. Perfect. Yeah, not bad. 5 iterations. I don't, I do not know why I need to input the default values since those are default values of our bracket right here. So I guess we just put them in. So try putting those in and changing the name of your bracket and it'll work. I have nothing else to add to that, but yeah, we're done here. So let's look at our unknowns. Okay, so we have the actual values of our unknowns that we need to, well, now we'll use the McCabe field to actually plot this out since it doesn't really matter right now as they are. So currently we have liquid flow rates, vapor flow rates, so correspondingly first 4 rows and our temperatures. So it looks like very different from what we had our initial guesses at, which makes sense. So let's see here. Eventually I'm going to be needing copy pasting all of this, but I'm going to be deleting most of it too. I just want the staircase here for the McCabe feel, the 45-degree line and the update layout, and then this is the equilibrium. Equilibrium we grab, so this was from Panchon Savret, which the equilibrium lines came from right here. We've done this plenty of times in the past. I'm just going to opt out and say this is free for me to use. So this is the equilibrium points. We have linear space points that, and then we store them. Well, we store lists for temperature and our Y1s, and using the bubble temperature and RTL this time, which is we coded it earlier. Again, we did this previously. I mentioned that before. We have a composition made up of all these spaces, space points, linear space points at a constant pressure. And using our bubble temperature, we grab our temperature and our vapor mole fractions, and we store those correspondingly. This is just at pure equilibrium. What's next? I think we have this. We've done this in the past before. I'll actually use the drawing I used for this, which is actually kind of helpful, but we'll need to, after we get our X and Y's from our liquid and vapor flow rates, we'll need to order them in a paired manner that matches our staircase that we've seen before. So I actually won't be using this, but just to show we've done this before. This is dynamic distillation for process and dynamics. We did a dynamic distillation with changing reflux ratio, and we actually had multiple McCabe field plots. So we won't be doing that, but there's a similar idea here, so I'll get rid of that. First thing here is, actually I can get rid of scalar bracket. I'll need those. Oh, I'll keep them open. What are we doing? Wow, this is a long video. Okay, so let's try to get this done. Let's unpack our X and Y's. So to do that, we've done that plenty of times before. I'm not going to try and make a mistake here. I'm going to use something that works. So here. I don't think we need all of this, but I'll delete and use what I need. So control left bracket to left indent, and I delete everything. Now this is for our unknowns, and we do it for all the values. We split them every row, and we take everything except the last row, and we do a split for 2, and I think that's it, right? So let's check that out. Can I just take this, see what it looks like? I always get confused here since this is a little bit new for me. So we grab the liquid flows, 4.15, 8.1, 8.7926, 5.029. So did not quite. Looks like it split it in half across rows. But actually we want it in terms of axis 1, so it splits along the columns. So let's try that again. There we go. That makes more sense. So 4.1, 8.7, 4.03, 9.5. There we go. So it's cut in half here. So we split it along the columns this time. So that's what this axis 1 is doing. Don't be split. Yeah, we have axis 0 there. So do I want to try? Sure, why not? I tried it earlier, so I think it's like this, so I have an extra one here. So let's go 2, 3. What am I doing? 2, 3, and then 3, 4. And then say I want to split that up. So NP split J into 2 cross axis 1. So notice that if I order them how it looks like in the unknowns, it's split it across the columns instead of the rows. So 2, 3, and 3, 4 are now column vectors. So versus if I did it, it'd be 2, 3, 3, 4 with axis of 0. There you go. That's my quick example that helped me understand it. But anyway, so now we have that. Now we have the proper liquid and vapor mole fractions. Do we want this up? Sure. Now we want to acquire the liquid vapor mole fraction. So this was the flow rate, so I don't know what I'm saying. Now we want the fractions. So to do that, this would actually work, but it's not technically correct since this is actually one value, and we, for vapor mole fractions, we want, or mole fractions in general, we want them in pairs going across the entire column, not just for the one value. So if you look at this, it'll take the sum of all the liquids and give us one value. So this X will be extremely small. And that's not what we want. So to do that, we use, what did we use? I already forgot. It's also axis 1, right? It's this whole idea of axis 1. And this will actually not work because it needs to broadcast. So 10, we actually have 10 values of x's. And it needs to broadcast a 10 by something, I forget. 10 by 2, right? So yeah, this is 2 values. And then our broadcasting is 10. We want to change that. We want to add an axis of 1. So we've done that before. But I don't remember. I think it's column and then none. So let's try that. Oh, that worked. What are we looking at? Wow, we got values. Perfect. So that looks about right. Higher for the more volatile. So this is ethanol, and more of the water on the lower stages, which makes sense. So not bad. I'll put X there. If I copy this. So we do the same exact thing. We do axis is equal to 1 and add that, add an axis of zeros so it can, or add axis of 1s, I guess, so it can broadcast. Make sure it's not commented out. And let's take a look. So we only want to do this for the more volatile components, so we'll be grabbing the first pairs. So all of these arrays. So we can just map that exactly as is. Technically we should use a new variable, but I'm trying to be fast here. 2 hours, so let's see. What is it like? We can unpack it. And it would be the current X for all the values except we want the first column only. And the same exact thing for the Y. Did I do that correctly? We'll find out. All the rows, and then the column is only the first element. What's happening? There we go. Wow, perfect. So we got 82396, 80805, perfect. We grab the first values of each pair for our X's and Y's. So now the hard part, not really hard part, but I showed that before. I deleted it. So here. Nope, I already threw it away. Was it dynamic distillation? Yeah, so that comes from dun dun dun. You've done it before. Surprise. Right here. So right there. Good thing my past self can teach my current self. So I drew this out for a previous video for our staircases to show how would we grab our paired points given, goodness, what's happening. It won't let me go to the right anymore. Maybe. I might have to go on the iPad and see. Process, and this is, I don't even know. Let's see. Homework 3 parts. I'm just gonna. What is going on? It's too late for this. Okay. Right here. So we have pairs of points. We know that our first pairs of points are equal since they start on the operating line. So those must be the same, but remember our unknowns contain only stage 1. So for the vapor mole fractions, we have to repeat that at the top for our x's because those are the same. Since we start at stage 1, technically the condenser is the equal vapor mole fractions because what comes up must come down as the same composition. So technically x0 in this case, so x0 right here, and y1 are the same, and we have to repeat x0, which is not currently in our list of x's, as y0. So for our y's, it looks like we repeat ourselves, since looking at our staircases here, we only repeat our y's as we go across here. So y's are repeated, and then x's are a little bit staggered after the first x. So after the first x, it's different from the second x, which gets repeated, repeated, and repeated. So repeated x, repeated x, repeated x. And then the last x here is actually not repeated. So notice how it does change at the very end there. I kind of wrote over all my drawings there, but key step here for x's, we add the x that is equal to our first element of y, the first vapor mole fraction, since they're equal. Again, from our condenser, they're equal compositions. And then we add in our last x. We don't repeat our last x, so we have to add that back in after we do the numpy repeat. And then for y's, we just repeat them all. So let's see if I can remember that, since it's not really wanting to show up here. Do I want to split it? No, that's fine. I explained it decently. So we can say something like x plot, maybe. x1 plot. Sure. So numpy concatenation. We said we add in our first component of y since they have to be equal. Remember, this is starting at stage 1. So if we want stage 0, the condenser, this is repeated. Since those y's are the same for that first staircase. So y0, and then we repeat everything except the last. So for x, we repeat everything except the last value, everything except the last value, bracket -1. What am I doing? Not -1. Repeat them twice, and then we add back in our index of the last value since it wasn't repeated. So let's look at that. So this number should match how much we have for our y's, 20. Beautiful. I'll go in full screen here just in a bit so you can see it matches up. But then for y's here, oh, I'm getting tired. Y, we just repeat, so don't really care about this. Still a bracket because of concatenation. Don't add anything in the front, and we just repeat everything for the y, and including the n, according to our drawing here. Can't even see my there. According to our drawing here. So, V cursor again. Okay, and let's take a look. Actually, I want to see the shape first. 20, please. Perfect. Hey, next lab, full screen. Get rid of axis, get rid of split. We're almost there. Now, believe it or not, we have our points that were of our staircase. And we also need our equilibrium, which I didn't copy paste yet. I now will. So now we have our x1s and y1s for our equilibrium curve. And now all I need to do is do this. Copy paste for our figures so I don't have to waste time typing this all out. Done this a million times. Fig 1. I don't have stripping lines. I don't have Q lines. I have a staircase, 45-degree line, and let's see. So this is actually our equilibrium line. Equilibrium line. So that is x1s and y1s. So I actually flipped them. So x1s, y1s, and then I said our staircase is the plot. x1 plot and y1 plot. x1 plot and y1 plot. This one more here, x1 plot, y1 plot. So this line of code is for our labeling of our staircase. Each point, you'll see how many steps we take. And I think we're good. Shift enter and we're done. Please. Wow, let's make it bigger. We're done after 2 hours and 30 minutes. Oh my goodness, that's beautiful. So we get bunched up a little bit, but we make it past our operating line pinch point, and we end up getting a good separation. Again, notice for ethanol, we are more concentrated in the vapor fraction compared to liquid fraction, of course at lower liquid mole fractions. And it took about 10 steps to get here. So trying to be fancy, but I don't know how many times we've plotted the McCabe deal at this point, but there you go. We've solved our mesh distillation column. So I'm not even going to try to summarize this, but let's check off everything we did. So we kind of derived and implemented them at the same time for our mesh equations. Wow, it's the white mode anyway. And then we applied it. So that kind of came with the Jacobian, evaluating our equations and getting the Thomas algorithm. So that was the actual Jacobian, where each of the ABC coefficients in our, not coefficients, but values in our original Thomas algorithm were now 5x5 matrices, and kind of made things a lot more difficult. So we had to treat things in terms of matrices. So kind of skimming over the functions. We evaluated all the stages for all their equations, took the partial derivatives with automatic differentiation respect to all the unknowns. We evaluated those equations from our initial guesses right here. And taking the norm, we had to evaluate that, condensing our problem into a single value compared to a tolerance. And if it wasn't above that tolerance, we kept reiterating, doing our block tridiagonal with the Thomas algorithm, solving for a delta unknown, and bracketing and minimizing our unknown so we could see how much we needed to move our current place value. So it took us 5 iterations. We managed to get pretty well under the tolerance after that. And after we have our unknowns, we extracted our values for liquid vapor flows, got our liquid vapor mole fractions, combine them into staircases using the methods we've done previously, and also using the equilibrium points. So for a non-ideal mixture, we used the bubble temperature and extracted those x1 and y1 equilibrium points to graph this curve. And then with our staircases and my little label maker here, we finally graphed our McCabe deal. So that's my 2-minute, however many summary. But yeah, this is the final video. So this longest video, the most calculations, kind of combining everything we've learned so far into one gigantic mess of code. But it all worked out and we got our answer. We solved our distillation column and we got our XY diagram and McCabe deal. So thanks for watching this final video. Appreciate it.